All right, so page 31, we started talking on Thursday about conditional probability. And the two main ideas or subtopics would be dependent events versus independent events. Okay. I want to make sure you understand the difference between conditional and mutually exclusive events, because sometimes students mix them up. So where's my scrap paper? Maybe I'll just give you a quick glance at what is the difference. Here you go. So when we're wondering whether or not events are mutually exclusive, right? We're wondering, if I consider my universal, is there overlap between those events? So for example, a sum of 7 or a multiple of 3, let's say. We should probably do sum of 6. Okay, and a sum that is a multiple of 3. There is something in here. There's instances where you're double counting those events. So that's what we're interested in. Okay, whether or not we're double counting, do we need to adjust for this and subtract the overlap or not? So mutually exclusive, by definition, this would be mutually exclusive right there. This would be ME. Yes, this would be not mutually exclusive, right? Because there's an overlap. When it comes to conditional, we're going to be interested in, there's an event that happens first and another event that happens second, okay? And we're wondering, is this going to affect the second event? For example, you're going to see that right away. If you have 52 cards and you take one away, right? No replacement. If you don't replace it, you're going to be left with 51, right? 51 cards left. So the first event, what happens first, you drawing a card, is going to affect what's happening next. And this could continue on, right? If I went around the class and everybody grabbed a card, every time somebody grabs the card and it's not replaced, the probability for the next person changes, right? So this is what we're dealing with here. We're wondering, is what happens here, is that going to affect my second or not? Okay. I can tell you this. I usually have a little. There we go. Die. Why not? For example, if you're rolling a die, right? What are the chances of rolling a 4? Would be 1 out of 6, correct? Will what happens here affect me rolling it a second time? Will this have any say on the second time? No. It's still 6. It's still going to be 1 out of 6 every time. Okay. However, I'll deck of cards here. That's different. Deck of cards, you have to watch for the wording. Okay. If somebody grabs a card, doesn't put it back, it does affect my second event. But if somebody grabs a card, looks at what it is, and then puts it back in the deck for the next person to take, it would still be considered independent event. The first one will not affect my second outcome. Okay, so that's what conditional probability is more interested in. So they are different. Okay, I'm not going to mix them up. Mutually exclusive is more like, are there outcomes that are the same? Conditional is, does the first one affect my second one? So I hope that distinction makes it a little easier to grasp the concept. Okay. So here we go. There are my props. So on Thursday, I had probability of rolling a 5 and rolling a 3 with two 6-sided dice, right? And so that's what we looked for, probably a 5 and 3. This is the probability tree, not the number of outcomes tree. So there's always something happening, something not happening. So rolling a 5, not rolling a 5. And then we had rolling a 3, not rolling a 3, right? But then at every branch, right, we actually multiply. And is always multiplying. So 1/6 and 1/6 there's 1/36 chance of you rolling a 5 and a 3. Okay? That is your probability. You could turn that into a decimal if you wanted to. Then you have probability of rolling a 5 but not rolling a 3. Probability of not rolling a 5 but rolling a 3. It just flipped, right? That's 5 out of 6. And then probability of not rolling either one is the highest, right? But remember, and we multiply. Okay, so there's two things here. We're going to multiply the probabilities, but we're also going to have our tree diagram to show that. One more thing here, guys. If you have a highlighter, I will ask you to say, to make a distinct, right? Every single outcome state out of 6. Okay? Total outcomes not affected by first event. Okay? Exclamation mark. Should I zoom in? Yes, I should. Okay? And so, so this scenario here, because of the total not changing, I'm going to write on the side here independent. This is very, very important. You make note that these are independent. How do you know that? Because I can clearly see on this tree diagram that nothing has changed from the first event. The first event did not affect in any way what happened next. This is the most obvious scenario. It will change. Okay? So, when probabilities are independent, when you've determined they're independent, probability of A and B happening is simply taking their probabilities and multiplying them. Okay, that's it. So when I say or, I'm just flip-flopping the A and the B, the order. So if this throws you off, don't worry about it. Okay, this throws you off, don't worry about it. But its probability of A and B happening is PA times PB. All right, so keep that in mind. I'm going to go over to 32 now, and now we're going to look at dependent events. Okay, if the first event affects the second event, and so forth, we say that these events are dependent. Okay. Consider a standard deck of cards. Geraldine draws one card. I'm going to use a different color for this one. Does not replace it. Does not replace it. Why is he saying it so many times? That's giveaway. That is a dead giveaway. If you're taking away from the total for our next event, you're affecting the next event. So they're dependent. They depend on each other. You know what I'm saying there? Then draws another card. What's the probability of drawing an ace and a face card? Okay. So it's asking for probability of ace and face. That's what this question is asking. Okay. I like this tree diagram just because sometimes it does show up. Okay. So the first event is ace and not ace. That's what we're considering first. Okay. So what's the probability of drawing an ace? There are 4 out of 52 correct. And therefore, how many non-face cards? 48 out of 52. It's gonna get too messy, but you could have done the decimal. You could have just stuck to decimals because sometimes there will be instances where that's what you want to do. So if you rather, I'm going to go 0.0769. Okay, that's my decimal for 4 out of 52. That's just fine. This one would be what? 1 minus that, correct? This is 1 minus that, or just 48 out of 52. It's up to you. But these two add up to 1. Okay, so this is 0.9231. Together, they add up to 1. Okay, you should be able to always say, hey, the sum of these two probabilities, it happening and not happening, is always 1. That's something I need you to remember when you do one of these. My second event is face, right? So you can go face, and then on this branch here will be not face, and then face, not face. Make sure you put the bar on top of not face, okay? I'm going to put the probabilities as a fraction every single time. Now, because this happened and it has not been replaced, I have 51 cards left every single time. Okay, that is that dead giveaway that these are dependent. When you notice, hey, wait a minute, the total has changed, it's a dead giveaway. Okay, if the first one is an ace, you grab it, you still have 4 faces left. Okay, right? Because the ace doesn't take away from the face. Got it? You understand what I'm saying? Slow down, Mr. If you go down this branch, and the probability of grabbing an ace is 4 out of 52, right? If you travel down this branch, then you are going to grab an ace, right? So now one of the aces is gone. You're down to 3 aces. Does that affect the number of... Oh, I know why you were... I know why your faces were like... There are 12, correct? That's why you were complaining. Okay, got it. Sorry, guys. I wanted to see your faces. How many faces? So face is 12 out of 51. It's still 12 out of 51. Here, even if you're not grabbing an ace, you still have 12 faces. So the total, sorry, this is 40. This is 40, sorry. So the amount of faces doesn't change, but the total has changed. Okay, so I want to make note of that. But this isn't complete yet. I would like to say that on this branch is probability of ace and face. It's 4 out of 52 times 12 out of 51. This is probability of ace and not getting a face. 4 out of 52 because you're going down this branch, and 40 out of 51. Probability of not grabbing an ace. Yeah. Here, because I have a deck of 52, so if there are 12 faces, then there are 40 that are non-faces. Make sense? Yes. Yeah. Just like here, 4, I take that away from 52 to get 48. Actually, a good question. Sometimes I turn these into a decimal, but now I'm just going to keep it like that. Not ace and face. Not ace. So that would be 48 out of 52 times 12 out of 51. And then probability of not getting either one is 48 out of 52. and 40 out of 51. So I'm always just traveling down the branch, because and getting this and that, you got to multiply those probabilities. Okay. What is this question really asking us for? If you look back up here where my pencil is pointing right now, it's asking for probability of ace and face, which is this one right here. This is really traveling down this path is all this question was asking for. And you're like, why all this work, right? Because I need you to see that, because down the road, there might be other ones, right? Other combinations they're asking you for. So let's do the 52 times 51, because that's going to be a common number, right? So 2652. Sure, you could reduce it, but for now, we're just going to leave that. So 4 times 12, that'd be 48. 4 times 40, that's 16, right? 160. 48 times 12, 576. 48 times 40, 1920. Let's turn them all into a percentage or decimal, whatever. I'm just gonna quickly get that. That's 1.81%. This is 6.03%. 2172. 7240. You know what? I'm just double checking here. 1.81. Yeah, we're good. I'll be right with you.
About the not space, 51 minus 12 is 39, so why would that be?
That's right. That's what it was. That's why this wasn't adding up to 100%. That's why I was like silent for so long. Thank you. I appreciate that. Can I do this again? So you follow 4 out of 52, 48. Is that where you were asking me why I got 40? Because it's 51 minus the 12. Thank you. My students are so much smarter than me. I like it. Yes. So this is 39 as well. That's when you go off script. Don't do that. Okay. See, yeah. I hope you didn't use a pen here. That's why I was like sweating here. I'm like, it's not adding up to 100%. So this is 156. And then 48 times 39, 1872. 7059. And this one, make sure you make those corrections because 5.88. There we go. Okay, so make this a learning opportunity, teaching moment for me, humbling moment. But yeah, what I was doing is I was adding these up, and I always do that just to make sure, because if you make a small mistake, you can catch it here. So now it adds up to 100%. Now I know we're okay here. Another way you could have checked is adding up the numerators and make sure they add up to 2652, right? Because you got to go 2652 over 2652. That's another way of double, triple checking. So yes, thank you. So right, so you can check this way, you can check that way. No matter how you go about it, there's a way to making sure you got this right, this tree diagram. However, this is really all that we wanted, okay? This one right here is all that this question in particular was asking for. Okay, and I think I just want you to focus in on this. You could have done this without the tree diagram, of course, right? You could have been like, well, grabbing an ace, 4 out of 52, grabbing a face card, well, there's still 12 left, and 51 remain because this one affected my second outcome. So you didn't need this. You don't go and do this every single time because you're going to waste way too much time. But sometimes I will ask you to use a visual representation. The province might ask you to do that too. So you need to be comfortable coming up with something like this. Okay. The province could also ask you, what's the probability to have at least one of them? At least one of them. If it asks you for at least one of them, you would consider this one, and this one, these three. You would not consider this last one. So this would be a good candidate for doing indirect, like 1 minus both of them not happening. Take that away from 100, and you would essentially come up with what these three are added up. So always keep that in mind. That's always a candidate there for you to explore. Okay, so dependent events. Total has been affected by first event. Okay. It is therefore that we have to use a different notation. Okay, we have to use a different notation. The probability of two events when they are dependent, when you know that the events are dependent, we use this formula. Okay, so I just need you to understand this more so than memorize. I mean, I still want you to have that on your study sheet. To be honest, I would just have one of those versions, not both. And I need you to know how to read this, okay? So I have it down here. Probability of A and B is going to be probability of A happening given that, right? So times probability of B given that A has already happened, okay? This is like nerdy mathematicians would read this like, oh, okay, they're talking that they're when I see this, it's telling me that the first event affects what B is going to be, like that second event. Okay, so this bar A, right, is saying, hey, find the probability of B given that A already happened. Okay, so this is what it actually is saying. Find the probability of A and B happening is equal to probability of event A times the probability of event B, and here's where I'm going to use orange, given that A already happened. You should be able to determine when two or more events are dependent by considering whether or not the total possible outcomes are being affected when one event is performed before the other. The key word you will encounter again, right? The key word is items are not being replaced. Okay. I'm going to give you a variation of the formula above. This one, folks, is just me using this one and just shifting it. Like if you wanted to know just this one, you would divide both sides of the equation by P of A, right? And so sometimes you might want to use this version of it. Okay. And I will give you some examples so you can know when to use this one. But to be honest, you could just always stick to this one, plug in which ones you know, and then find the other one. Okay. All right. You're with me, right? Let's go back up to this ugly tree diagram that I made here, right? Could have been a lot nicer with all those mistakes there. Look at all that smudge in there. If this had been independent, what would have been different here, guys? It would have, the 52 here would have followed you up to here, right? All of these denominators for the second event would have been 52 as well, because you're replacing the card. Okay, so that's how this is different. We would actually just say, hey, this is probability of A and B is just probability of A and probability of B, nothing changes. Okay. All right, let's go to page 33 and do some without tree diagrams. Because let's face it, we could do without them. Okay. Here you go. There are 3 green, 2 red, 4 blue marbles in a bag. You're drawing 2 marbles in a row. This is very important. Okay. 2 marbles in a row. Answer with and without replacement. So I want you to think of you replacing them and you're not replacing them. So what I'm going to do is I'm going to split this page right in half here, 2 columns, all the way to the bottom here. And I will call this replacement, replaced, not replaced. What else can we call this? Which one would be the dependent column? This one, right? If you're not replacing dependent events, okay? If you are replacing, it's independent. That's also that we're saying the same thing. If just using different terminology. I think most of us would be more comfortable with, hey, replace, well, nothing changes. Not replace, boy, wait a minute, something changes, okay? Okay, picking a green marble, so green first, then a red marble. Okay, well, let's figure out our total here first and foremost. That's 5 and 4, that's 9, right? 9 total is probably a good one to remember. I want you to think of it this way, okay? Probability of green and red it's asking for. So under these circumstances, because things are replaced, all I'm going to go is PG and PR. That's it. I don't need to change the notation. It's just probability of green times the probability of red. I don't have to worry about anything being missing, okay? So you're going to go like this. Green, we have 9 total, and still 9 total for the second event. We have 3 green, and we have 2 reds, just like that. You can reduce if you want, but I'm just going to go ahead and go 3 times 2 is 6. 9 times 9 is 81. Oh, sorry, 81, not 91. There you go. Okay. 3 goes into both of them. So you've got 3 goes in there 2 times. 3 goes in there 27 times. And there we go. And you remember the trick, right? The math one. Math 1, does that work? Yeah, 2 over 27, there we go. Or you can turn that into a decimal or percentage, right? 0.0741 or 7.41%. But 6 over 81 technically would have answered the question. Okay. Now, not removed. So consider this exact same question, not replaced. I don't want you to look at this formula. I want you to think of this one. Probability of G and R. See if you can follow this pattern. You take PG times P of R. But what are you going to change here? Given that G happened. That's how you have to write it. That's if I give you this, like, hey, what does this mean? Oh, this means that the events are going to be dependent, that the first one affects my second one. So let's go for it. PG, we have 3 out of 9, correct? For the second one, how many are left if I don't replace what happens first? Because a card is drawn. It's 3 out of 9 chances of you getting the green one. Now it's going to be down to 8, right? And I still only have 2 reds left. So this is going to be 6 over 72, sorry. 6 over 72, which turns out to be 0.0833 or 8.33%. Notice that the probability is actually higher for dependent because when you remove it, the chances of the second one slightly go up slightly, right? So overall, it's higher here. Let's do one of these here. I hope yours isn't as messy as mine. Can I ask you to try the next one, 2 blue marbles, and use the notation as well? Copy it. It's 2 blue marbles, so it's actually a bit of a different spin. You're also going to have to watch your numerators, not just your denominators. So the first one is a blue. What's the probability of getting another blue? So blue and blue. I'm just going to ask you to try B and C. Just use a pencil, because if you're like me, you make mistakes probably, right? I've shown you how to do that. So again, you don't have to do a tree diagram, only if I ask for it, okay? 2 blue marbles. So probability of blue and blue. To be honest, on a test, I would not really care if you know how to do the notation, as long as you show me the work. Okay? But I need you to be familiar with it in case I present that to you and you have to read it. Okay? So probability of blue, we've got 4 out of 9, and another 4 out of 9. So it's just 16 over 81. That would be it. That is, if you're interested, 0.1975, 19.75%. Not that you need to do that, but in this case, but I would still encourage you. So probability of B and B under this scenario, it's probability of blue and probability of blue given that the first one was blue. Okay, so you have 4 out of 9 to start with, and guess what? Now you have only 8 left, and because the first one was a blue one, you're down to 3. So watch the numerator. Okay, so this would be 12 over 81. No, 72. There we go. I'll just leave it like that. Okay. For now, blue and green. I think we're okay. We're good now for the right. This would be 9. 4 out of 9, and then green. We've got 3 out of 9, and so that's 12 over 81. If you don't replace them, right? We have 9 and 8 left. We have blue at first. The greens are still staying 3, so the greens are not affected by the first event, so that is 3. So that'd be 12 over 72. Okay, so that's how you would do that. Obviously, you could reduce that. One more here, 2 greens. I'll do the notation here. G and G, probability of green times probability of green again. So we've got 3 out of 9, 3 out of 9. Technically, you can reduce that. It could be 1/3 times 1/3. So that'd be 1 over 9 if you reduce it. Or 9 over 81. That's okay as well. This one would be P, G, and G. But because you're told events are not, or you're not replacing, it's G given that the first one was G. So that would be 3 out of 9 and then only 2 out of 8. Okay, for the second event. Does that make sense? Right? So your number of greens are dropping and the total is dropping as well. So this is this like super dependent events? No, there's no such thing, but it's still something to keep in mind that sometimes both are affected, right? What about light colored? Let's say this ever shows up. What you here you have cases. I don't know if you've realized that cases. You have probability of green and green. I'm going to borrow from the top, by the way, because I've already done some of these. You've got probability of blue and blue, or you've got probability of red and red. You would just add those up. G and G, did I do that already? 2 blues is done, so I'm going to copy that one. That would be 16 over 81, or 0.1975. Red and red, no, but green and green is done. It's 1 over 9, or 9 over 81. How about I'm going to keep the 9 over 81 part, because this gave me 9 over 81 here. So I'm just going to keep them all the same. I'm going to write it as a decimal as well. This is 0.1111. Red and red, I haven't done that yet, so I have to do that here. So it'd be 2 out of 9 times 2 out of 9. So that's 4 out of 81. That's 0.049. 494, and then you would just add them all up. That's 0.358 or 35.8% chance of getting two light-colored marbles. How would that be different with the other if it's replaced? Or, sorry, removed, not replaced. Cases again. Okay, so probability of green and green, that's already done here. That's 6/72. Probability of blue and blue, and then probability of red and red. Blue and blue we've done already, right? That's 12/72. Red and red, I have to do that real quick. 9, 8. We've got 2 reds and then just 1 left. So that'd be 2/72. So that's 12 and 6 is 18 and 2 is 20. So it's really 20/72. That's 0.2778, which is 27.78%. So they are different whether things are being removed or not. They are different. Okay? So no tree diagram. Just show me when it's and you're like, hey, things are not being replaced. That should be like a ding, 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 right? I have to be careful with my denominators in particular and maybe my numerators. One more go using cards, okay? So go to 34. Oh, it's stating odds as well. Yay. Thank you for making my Monday, right? 3 cards are being drawn, one after the other, without replacement. Even if you're asleep, right, you should be like, oh, okay, what does that mean? Dependent events. That's what that means. Number probability of drawing a red card, a black card, and another red card. State the odds as well. So all of these are not being replaced, so we don't have to worry about independent versus dependent. We know these are all dependent. So let's go for it. A red card, so we've got 52, and then we're going to have 51 for the second card, and we're going to have 50 for the third card. Is that safe to assume? Right? I think that's pretty safe. Now we're going to have to be careful with the numerators. A red card, we've got 26 red cards. Okay, good. A black card, did the first event affect the number of black cards? No. Okay, so this is good. This is second. And then another red one. You gotta watch out. So the denominator is good. This is a red, this is a black, and another red. So we're down to 25 because this already happened. Okay. This affects that one, right? So there you have it. Now just multiply it all across. So this is 3 events, no problem. This times this times this. By the way, could we use permutations here? You could go 26 squared times 25 over, how would you write this in permutation notation? 52, pick 3, remember? What? Say what? You don't have to do this, okay? Don't worry about it, but it's still an option, okay? So 26 squared times 25, that's 16 900, 52. I think it's quicker, and on this calculator, it's quicker to just multiply those three numbers if you ask me. 132, 600. Trailing zeros you can always cancel, right? 1 to 1, like that. So 169 over 1326, like that. We'll just leave it like that. Odds. Uh-oh. How would you, when you have probability, odds are actually fairly straightforward. You would just go 169 here. The odds of that happening would be 169 to 1326 minus 169. And so that's 1157. And remember, these two should always add up to your total on your probability denominator. If these two don't add up to this, you're in trouble. Unless, of course, you simplified your odds, but if you simplify your fraction, you should still get that. Try B, C, and D on your own. See how well you can let's slowly take away the training wheels. See how you can do that. Maybe worry about the odds later, right? Like right now, I'm just curious, do you know how to set up this problem and figure out your probability of those three things happening in a row, okay? One, then the other. It's not happening at the same time in a row, okay? How are we doing so far? I've been doing it quietly in the background. Red queen, there are two of them. A black, drawing a black ace, two of them. And then a face card. You have to wonder, did you have a face card before at all? And a red queen would be a face card. Okay, so you're down, you take away one of, so some students might take away two. Remember, this is the probability of getting that one, but you're only drawing one card here in the first event. Okay, so you're down to 11. So that's your answer there. I didn't do the odds just yet. So black jack, red jack, and then a face card. So here you take away two cards because the first event is a face card, the second event is a face, and so you're down to 10 face cards. Okay, so that's what this ends up. So the denominator should definitely drop by one. The numerator, you have to be very careful what happened before. Okay, next, I'll do the odds in a bit. Ace of spades, so again, three events happening in a row. So it could be 4, 5, whatever. Usually 2 or 3 is the max you can expect. don't, it could be a deck of cards of 40, so watch out for that, right? Like whatever the question says, but if it doesn't specify, it's 52. I'm thinking of textbook. Textbook always gets creative with that. Ace of spades, there's only one. Ace of hearts, only one. A red card. The heart, this is a red also, right? This is red. So you're only down to 20, you're down to 25 red cards because the spades is a black card, right? So black, red, right? So this red card will affect the 25. So this is 25 over 132,600, okay? And here are your odds. Let's go back up. So this would be 44 if you use that to 132, 5, is it 556? I think, yeah. That's if you use the like this is not reduced, right? But nevertheless, there it is. And this would be 4 to 13,256. And this would be 25 to 132,575. So just a refresher on that. Okay, we're coming to the end here. I wanna, this one is, the next one is more like to prepare you for the lesson on Wednesday. Okay, so I'm gonna show you how to do that. I want you to recognize the wording and then be able to kind of know what to do. So let's go to 35 here. I actually don't necessarily want you to use this formula as is. You can, but I'm gonna just stick with a different way of doing this. I'm gonna use this one. P of A and B is P of A times P of B, given that A already happened. This is the dependent probability formula. This is a variation of that formula. Okay, I like to use the original. So a jar contains black and white marbles. 2 marbles are chosen without replacement. That is your giveaway. It's like, okay, we're in the dependent probability territory. The probability of selecting a black marble and then a white marble is this. Let's give it a different color. Selecting and a white marble is this. Let's do a bit of an inventory on the sides there. Probability of a black marble and a white marble, we're told is 0.34. Okay. Then the next part says the probability of selecting a black marble on the first draw is 0.47. So we know that this probability of black, like that happening first, is 0.47. Okay. So here's my green part. And here's the orange part. I got it straight from the text. All right. What is the probability of selecting a white marble on the second draw, given that the first marble was a black marble? How would you rewrite this using the notation we've been studying here? They're asking for this. What's the probability of getting a white marble, given that you got a black marble on the first draw? That's what the question is asking for. And you have to be careful with the order. If you had B first and then W here, that means that probability of drawing a black one, given that you already drew a white one, right? So you got to watch out with the order. So let's use this formula right here, guys, to solve for the unknown. Probability of black and white, I know, is probability of black, because we're told that's first, and then probability of white, given that a black one has already been drawn. We know this part. BNW, that's 0.34. We plug that in. PV is 0.47. We plug that in. And this is what I will call X here. So we don't have to rewrite that every single time. So what would you do in this scenario? You should probably realize this is just as simple as, hey, we're going to divide both sides by 0.47. That's all. That's all we're going to do. This cancels out. So let's go 0.34 divided by 0.47. That's 0.7234. Therefore, probability of getting a white one, given that the first one was a black one, is 72.34%. That's all that this page in particular is asking you to do. Do an inventory of what you have. Some of you might not even, most of you probably won't even bother doing this. The highlighted part here. You will just come up with the equation. You got to watch out, is this right? Is this the way it's supposed to look? And then plug in what you know, solve for the rest. Okay? So I will ask you to do this. 35, 36. I'm going to put it off the top here. 35 to 36. I will give you some textbook. 350, 1 to 5. It's not very long. If you want more practice, like what we did before this page, there it is. On 36, there's also the stuff we did on the previous page with cards and stuff like that. So I will expect you to know how to do dependent probability on the quiz tomorrow. Okay, so if events are happening and there's no replacement, I want you to know what to do at that point. All right, guys? That's it. Thank you very much. Enjoy the rest of your day.